This problem involves conservation of momentum in two dimensions. The diagram on the right shows the situation just before and just after the collision. The law of conservation of momentum applies separately to the x and y directions. We write these as the final momentum in the x direction is equal to the initial momentum in the x direction, and the final momentum in the y direction is equal to the initial momentum in the y direction. Let's begin by writing out all these terms in the equation of conservation of momentum in the x and y directions. We'll use an uppercase O for the orange disk and an uppercase G for the green disk, and note that the disks have equal masses. We can now simplify these equations. First of all, since all of the masses are equal, we can cancel out the mass from all of the terms in both equations. From the diagram, we note that the initial velocity of the green disk is 0, so we can strike out both the x and y components of the green disk's initial velocity. The orange disk is initially moving only in the x direction, so we can strike out the orange disk's initial velocity in the y direction as well. Let's consider the y equation first. Since there was no initial momentum in the y direction, there should be 0 momentum in the y direction after the collision as well, which tells us that the two remaining terms have to be equal and opposite. We can write the y component of the velocities of the two disks as their velocity times the sine of the angle their final velocity vector makes with the positive x-axis. For the orange disk, this is 37.0 degrees, and for the green disk, this angle is 53.0 degrees. We can then write the y equation as y orange final times the sine of 37.0 degrees minus v green final times the sine of 53 degrees equals 0. The minus sign for the green disk indicates that it's moving in the negative y direction. Solving this for the final velocity of the green disk gives us v green final equals the sine of 37 degrees divided by sine of 53 degrees multiplied by v orange final, or 0.754 v orange final. Now let's consider the conservation of momentum in the x direction. The x component of the orange disk's final velocity is just v orange final times the cosine of 37.0 degrees. The x component of the green disk's final velocity is v green final times the cosine of 53 degrees, and v sub x orange initial is just v orange initial since the orange disk is traveling in the x direction before the collision. We can then substitute for v green final from the y equation and solve for v orange final. We'll do this in two steps. First, factoring out v orange final, then solving for it. Substituting 5.00 meters per second for v orange initial gives us 3.99 meters per second for the final velocity of the orange disk. The final velocity of the green disk is 0.754 times v orange final, or 3.01 meters per second. We can now verify whether this was, in fact, a perfectly elastic collision by comparing the initial and final kinetic energies of the system. Recall that the kinetic energy of the system is conserved in an elastic collision. Before the collision, the kinetic energy is just carried by the orange disk and is 1/2 m times v orange initial squared. Plugging in, we obtain m times 12.5 meters squared per second squared. The final kinetic energy of the system is 1/2 m v orange final squared plus 1/2 m v green final squared. Plugging in 3.99 meters per second and 3.01 meters per second for the orange and green disks, we obtain m times 12.5 meters squared per second squared, which is exactly equal to the initial kinetic energy of the system. This was indeed a perfectly elastic collision. This problem involves conservation